All right, welcome everybody to the Paleoglaciers Working Group Winter Speaker Series. We have two great talks today about rock glaciers. Been hearing a lot more about rock glaciers as we've gone through the speaker series the last couple of years, and we're really excited to learn even more. So our first speaker is Olivia Stanley, who is a PhD student at the University of Colorado-Boulder, and she's working in the terrestrial hydrology lab with Dr. Eric Small. Her research focuses on snow hydrology, remote sensing, and hybrid physical and data-driven modeling to improve understanding of snowpack dynamics and water availability in complex mountain environments. Prior to her PhD, Olivia completed her undergraduate studies at Davidson College, where her research focused on soil science and fluvial geomorphology with Dr. Brad Johnson. She went on to earn her master's in geology from Idaho State last spring, where she worked with Glenn Thackeray, who's here today, to investigate rock glacier distribution and its hydrologic contribution in semi-arid environments. At ISU, her research combined remote sensing, field-based hydrologic monitoring, and geochemical analysis to assess the role of periglacial landforms in alpine water storage and stream flow dynamics. With her interdisciplinary background spanning hydrology, geomorphology, and environmental science, Olivia is dedicated to advancing our understanding of mountain hydrology, the cryosphere, and water resource sustainability in the face of rapid changing climate. Today, her presentation will focus on her master's research on rock glaciers in central Idaho, where she explored how these widely overlooked landforms contribute to late season stream flow and serve as cold water refugia in a warming climate. Take it away.
Perfect. Thank you so much for that introduction. So as Ben mentioned, I'm currently a student at CU Boulder working on my PhD and kind of living more in the snow hydrology world these days. But today I'm going to talk about my work with Glenn at ISU on rock glaciers. So the big question of this presentation is kind of, are rock glaciers water sources or water processors, or potentially, as we'll see, both? Yeah, I'll just go from there. And so, oop, can I change slides? Yep. Okay, so I would assume that most people in this group probably know what rock glaciers are, but just as a quick review, I tell people to think about rock glaciers as they would a typical bare ice valley glacier, except for that rock glaciers are obviously mantled by a continuous layer of debris known as the active layer. And so on the landscape, they look like what you see here, kind of glacier-like flowy landforms, but covered in debris. And they're easy to identify using aerial imagery based on their furrow and ridge topography. And then many times in the landscape, they have these oversteepened terminus. And in most cases, not always, but at least in the rock glaciers that I was interested in, you'll see these little meltwater streams that sometimes look more like a stream. Sometimes they're kind of seepy, coming out of the terminus of the rock glacier as well. And so there's only been a few studies that actually attempt to core these landforms. But in general, we think that they are climate resistant due to the active layer, that 10 to 15, sometimes smaller layer of rock debris that's mantling the entire landform. And so this active layer kind of decouples the internal ice core from the thermal dynamics happening in the atmosphere around it. And because of this evolving ice core and melting and seasonal inputs of snow each year, you have multiple hydrologic flow paths on top of, through, and below these landforms. Additionally, again, I'll get to this, but we think that rock glaciers are important because they act as both seasonal flow modifiers, but also long-term water reservoirs. And there was a paper that came out in 2018 that tried to quantify the global quantity of water contained within these landforms. And I'll talk about my feelings on whether that was accurate or not today. And so one of the main things that I want everyone to be on board with throughout the course of this talk is that rock glaciers are hydrologically unique, especially in comparison to other snow-fed alpine small streams that may be occurring in the same environments. And so one of the kind of motivators for the research that we went on to do in the summer of 2023 and 2024 was that we had this pilot data set where we had gauged a rock glacier stream and a nearby non-rock glacier stream. And what we were seeing was that in the snow-fed non-rock glacier stream, you see a decline in discharge throughout the entire season, which is this blue line here on this graph. And whereas the rock glacier streams are just persisting at this kind of consistent base flow throughout the entire period. And so this could have important implications for all sorts of water resource management that I'll kind of talk about in a second. But not only are rock glacier streams persisting in flow in a way that snow-fed streams are not typically doing, they're also really, really cold in comparison to these other alpine snow-fed streams. So generally, alpine streams will warm throughout the summer melt season in relation to ambient air temperature and a declining input from snowpack. Whereas these rock glacier streams are super cold and kind of persist at between 1 to 2 degrees Celsius throughout the same period. And so our instinct from these pilot data sets was that, okay, obviously there's something going on here hydrologically with these landforms that's important, especially when you think about the fact that bare ice glaciers in similar environments are declining at a pretty alarming rate in relation to climate change. And so again, rock glacier stream, non-rock glacier stream, rock glacier stream, much colder. And so what? Well, as I just mentioned, obviously valley glaciers and alpine glaciers, bare ice, are typical ones, are declining at alarming rates. And in places like central Idaho, we actually don't even have any glaciers persisting. There's only rock glaciers, but the rock glaciers are abundant. As you can see in this study by Johnson et al. In 2021, where they mapped rock glaciers all over the Western US, we have them all over the place in most of our like major ranges throughout the West. And so this could have important implications if they are in fact storing and releasing water in unique ways for general water resource management, for energy applications. If these streams are persisting in flow, whereas other streams aren't, they could be great targets for microhydropower applications, for irrigation and diversion applications. And then additionally, these are persisting at really cold, consistent flows. So are they possibly supporting unique cold water ecosystems that haven't been really previously acknowledged? And so we went out and monitored a bunch of rock glaciers, but one of the motivations for doing that is the fact that within the literature, there have been some hydrologic studies on rock glaciers, starting with this Williams study kind of in 2006 was a big one. But there have been some others in the American West since then. And my problem with all of these studies is that they're all kind of based on 1 to maybe 2 case study, big, beautiful, accessible rock glaciers. And that is not what all rock glaciers on the landscape actually look like or behave like. And so, to what extent is what the literature is telling us actually true for like how rock glaciers throughout an entire range would behave? And so that's kind of the guiding question and was one of the main motivators for me getting out there and doing all this field work and monitoring multiple rock glaciers in one range in one season. Not only are they hydrologically unique in comparison to other alpine streams, but are they unique in comparison to each other, or can we pick out some consistent patterns kind of across the board with all of these rock glaciers, even when we look at ones that aren't the big, beautiful type case rock glaciers? And so that's a guiding question, but then also we just want to understand how the hydrology of these landforms is really behaving as well. So some additional questions would be, how are the hydrologic characteristics of rock glacier streams comparable to adjacent non-rock glacier streams? What processes explain the distinct discharge and temperature patterns that we see in these rock glacier fed streams in comparison to those non-rock glacier fed streams? In the absence of data about the actual interior structure of the rock glacier, we're not going out there and coring these things. How can we infer processes of water flow above, within, and beneath the body of the rock glacier? And then, as I mentioned earlier, there's a question of whether rock glaciers are exporting long stored water and associated carbon. And if they are exporting long-stored water and carbon, could these landforms be acting as underappreciated cold water refugia, both in terms of the fact that they're really cold water, but then also have this old carbon that many of these kind of microorganisms seem to prefer. So to do this study, we traveled to central Idaho, where I mapped rock glaciers in the Lost River and Pioneer ranges, and then chose a subset, which you see in the yellow dots, to actually monitor. We installed hobo monitors, and then also I returned on regular intervals throughout the summer to dilution gauge to create rating curves, gather water samples, etc. And here I just want to make the point that rock glaciers are abundant throughout these ranges where we don't have any glaciers anymore. On top of the fact that we chose to look at both ranges because the Lost River Range is primarily limestone dolomite. It's a carbonate setting, whereas the nearby Pioneer Range is generally these older crystalline rocks. And so when I talk about some of the geochemical analyses, the isotopes, and the carbon analysis that we did, which I'll get to at the very end of this talk, it's kind of important to consider both ranges to understand the carbonate effect within these systems. And so I'm going to make 4 primary points that are going to inform our conceptual model of what's actually happening within these rock glaciers and how they're storing and releasing water throughout the season and over multiple years. And the first point that I want to make that I've kind of already touched on is that rock glaciers are persisting in discharge in really cold water temperature. This graph is from Dickey Peak Rock Glacier, which is one of the bigger type case rock glaciers, but it produces the prettiest data. So in the context of this talk, I'm going to show a lot of charts from Dickey Peak, but then make the point that I do have data from other rock glaciers that kind of back up these points. And so again, persisting in discharge, persisting in very cold water temperature. And when we look at the data throughout the winter, we see that, again, these systems are flowing even in the winter, and that water temperature is, again, staying at about 2 degrees Celsius, dips down a little bit during the spring runoff season. But yeah, remarkable persistence in both flow and cold temperature. And then again, when we toggle back to comparing this to nearby non-rock glacier streams, this comparison is Dickey Peak and a non-rock glacier stream that's about 20 kilometers away, but like same basin, same everything. You see this comparison where these systems are obviously diverging in characteristics from typical snow-fed streams. And so I show this, don't try to get anything out of these plots other than just showing that I monitored 7 different rock glaciers. We see similar patterns of flow persistence in very cold water temperatures in all of them. But the easier way to compare stream to stream is to normalize everything and to show you guys an exceedance probability curve in which we see flatter lines indicate a less variable flow regime versus the steeper lines show more variability. So these light blue lines, Cedar Creek and Lone Cedar Creek, are 2 snow-fed non-rock glacier streams, and you see that steeper curve, whereas the dark blue lines, ignore Fall Creek on the top, I'll address that in a second, are generally much flatter with more persistent flow. Fall Creek is a really big rock glacier in kind of a funky basin. I'm not going to really address that in this talk, but if anyone has a question about why this Fall Creek rock glacier stream looks more like one of the snow-fed streams, we can talk about that during the question period at the end. But the point I want to make is that the entire rock glacier data set supports this flow persistence and cold temperature. And so the next thing that we want to look at is still looking at the hydrographs, but we find that the responses of rock glacier streams to early summer rainstorms differ strongly from responses to late summer rainstorms. So on the left panel, this Dickey Peak in the red, that's a rock glacier stream. And then Cedar Creek in the yellow on the right is a non-rock glacier stream. And What we see is that in the beginning of the summer, these rock glaciers respond more slowly to incoming precipitation. There's a bit of a lag, and then the recession curve overall is much longer and more extended in comparison to the late summer response, in which you have an almost immediate response to incoming precipitation that's very pronounced, and that water flows through much more quickly in about like 24 to 48 hours. I have the Cedar Creek plots here. These were during the same exact storms. These streams are near each other, and you see that in the Cedar Creek stream, there's obviously much more water being processed by the basin, a slower release. You see a more muted response to incoming precipitation and much longer recession curves. And so we interpret this late season kind of extreme flow response as indicating more interconnectivity within the rock glacier itself, that allows, in a higher hydraulic head kind of to start with, that allows for water to flow through at a much more rapid pace. We can also look at conductivity within these streams. And so we see a steady increase in electrical conductivity throughout the season. And we take this to indicate that water being released in the later summer has undergone longer storage, whether it still be seasonal water or long stored water. But that water has undergone a greater degree of water rock contact, which would lead to that slow increase throughout the season in conductivity. And then finally, we did do some stable isotope analysis on these landforms to kind of get at that question of where's the water coming from? Is it seasonal, meteoric from that past year, or are we seeing some release of long stored water that's undergone multiple freeze-thaw cycles, etc.? And in the data set, we see that in general, rock glacier springs, and these include samples from the entire spread of rock glaciers that I monitored, generally, they're still plotting right there along the local meteoric water line. There is some offset in comparison to the non-rock glacier streams, and so maybe we are having some mix from stored water, whether that be long stored water or not. We don't have any ice cores, so it's hard to do like a pure mixture model with this. But we take this entire data set to kind of indicate that in 2023 and 2024, most of the water being processed by the system is still that year's water and that year's snowpack. And so that brings me to kind of this conceptual model that we've designed, in which rock glaciers are in fact short-term water processors that act as kind of shallow aquifers on the landscape, and then are also likely storing long-term water reservoirs, but there's still a bit of a question about how long that is, when the water is released. 2023 was a pretty large snow year, so it's also possible that we just like didn't capture any sort of meltout at the end of the season. But basic idea is that in the beginning of the year, you have mostly seasonal snowpack being processed by the rock glacier. Most of that water is either infiltrating into porous spaces within the ice and interstitial core of the rock glacier or into fractures. And then the rest of it's kind of running off over that still partially frozen active layer. And then by the end of the season, you have a more integrated system, more interconnectivity, and more options of flow paths for that water to flow through. And so we still think that most of the water in the late season, at least based on the data that we have, is just stored meltwater that's finally getting pushed through. And that we don't really have a huge contribution from a long stored melting ice core. And therefore, this system is acting like a shallow aquifer that may be storing long-term ice, but isn't releasing it on any sort of like concerning timescale. And so I mentioned, though, we're talking about that the water in 2023 or 2024 is primarily from that season, but are rock glaciers exporting old water and carbon as well? And so as kind of a side analysis, we, at the end of the season, went to all of these rock glaciers right where the springs are coming out and scraped biofilms from the rocks coming out of the rock glacier, or right at the base of the rock glacier. And we like to call this the water source paradox, because I just mentioned our isotopes indicate that we probably are seeing mostly seasonal snowpack being processed through by these landforms. And yet, when you date the biofilms that came off of, or that are growing right at the base of the spring, we do see some kind of old ages. And so, one thing I want to point out here is that in the blue, these are rock glaciers that are in these carbonate terrains. And so these are the Lost River rock glaciers, and we do get older ages. And this was all just kind of a pilot, we're curious if this would even work type of study. Um, but we also grabbed a couple biofilm samples from the crystalline rock glaciers, and we still get pretty old ages associated with those systems as well. So these rock glaciers obviously have some influence of stored water, stored, I'm assuming CO2 that's being released, but there's still a question of what's the influence of the carbonate lithologies on the apparent age of the carbon in the biofilms. And then we're also asking to what degree is the carbonate lithology contributing inorganic carbon to the rock glacier hydrologic system. So we did some additional isotopic analyses. And you do see that obviously we do have a degree of inorganic carbon existing in these systems. And right now, one of the questions that we're trying to kind of piece apart is to what degree do we have inorganic versus organic carbon in the systems? How is that carbonate or carbon entering the system? Is it particulate or dissolved? And it would be ideal to be able to do a mixture model to kind of get at this question, but obviously this is all still kind of stuff that we're wrapping our brain around. But exciting to say the least that obviously there is evidence that to some extent there is the release of old water and carbon within these systems. And so I guess I'll just wrap up with a couple of takeaways. Rock glaciers exhibit persistent flow and cold water in comparison to the non-rock glacier mountain streams. And so again, these could be kind of critical targets for water resources, especially in these semi-arid environments where water can be kind of scarce in the mountains. They are acting as both short and long-term water reservoirs in these semi-arid mountain ranges. I think that their importance is probably more associated with the way that they process water in the short term, but obviously knowing where our stored water is in the environment is going to become increasingly critical. And then the most exciting part about this study that I kind of see is that they are exporting cold water and old carbon, which could be supporting these unique cold water ecosystems. We actually found a couple of rare stoneflies at some of the streams, and so there's a question of, yeah, could these be cold water refugia that otherwise hasn't really been acknowledged? They're pretty isolated systems, etc. So, and that informs our like ongoing question. So obviously, I was talking about how I think these are more important in the short term, but how are rock glaciers persisting through climate change? One of my peers at ISU is now applying INSAR to some of the rock glaciers that I was studying. Another way you could get at this question is space for time substitution, so to study rock glaciers in various climate settings. And then the other question associated with the ecology is, again, what is the typical trophic structure of these streams? So it would be really cool to have more ecological surveys and extended carbon analysis to try to do some mixture modeling to understand contributions, relative contributions of inorganic versus organic carbon. And yeah, with that, I will thank Glenn and Colden and Bruce, who are other faculty members at ISU that were really critical in the ecological and isotopic components of this project. Many, many people that walked many miles in the backcountry in the field with me, and then my current PhD advisor, Eric, who's been really supportive of my continued work with the rock glacier community. And with that, I'll take questions.
Excellent. Thank you for that, Liv. We do have time for questions. So if you have a question, just turn on your microphone or raise your hand.
Hey, Ben, I've got one.
Go ahead, Jeff.
Olivia, hi, it's Jeff Monroe. This was just great. I really appreciated the overview and yeah, huge congrats for making it to all these sites. This is never easy work. I love the last slide or toward the end where you had the idea to try to date these biofilms. And my first thought was just like yours. I'm like, oh, well, the Lost River Range, they're going to give all kinds of screwball ages, but you have the Pioneer Range too. And they kind of all converged right around like 1500 years or so. So yeah, I guess, can you talk a little bit more about what you think that means? You mentioned it might be CO2 or something, but I think that's a really, really cool result. And I'd love to hear more about it.
Yeah, like I said, we only took like a couple samples. We had like a small grant to do a little bit of this pilot study, and we weren't really expecting to see much. And then to your point, all of the ages kind of converge around this like maybe a little bit earlier than Little Ice Age type of stuff. And so yeah, we're kind of piecing apart that question right now of like when did this ice, like how old is this ice? And like what time period would it have made sense for maybe these were bare ice glaciers at one point that then converted to rock glaciers? Because obviously a lot of people talk about the glacier to debris covered glacier to rock glacier kind of continuum. Um, I don't know. We're still kind of piecing that part apart. My thought would be that you would have inorganic, like old inorganic carbon and like CO2 bubbles or things that are held within the ice. But then obviously you also have a lot of like lichens and things like that growing within the rock glaciers. So what degree are you having preserved organic carbon within the system? There's still a lot of questions that honestly I haven't really like pieced apart yet. And so we're trying to have a few more samples. It would be really great to do like, again, an extended kind of isotopic mixture modeling analysis on this stuff. But for right now, we're just really stoked to see that clearly there probably are some old ages. And especially in those crystalline samples, um, I can't think of any contribution that would of old carbon other than like CO2 potentially that was like held within the ice core that's getting released as it melts out. So yeah, lots of questions there, but like kind of a whole area that a whole other project should probably tackle.
Yeah, every good project ends with lots of questions for the next project. Good stuff.
All right. How about one more? There's Doug. Go ahead, Doug.
Hi, Olivia. That was great. I'm sorry I came in a little bit late because I was still getting out of my classes, but so I missed the first part. You may have already talked about this some, but I'm also really intrigued by um, the some of your radiocarbon results, and wondering you just mentioned how there's really no source of obvious carbonate in those in the crystalline rocks you were working with. Was it feasible that there's, say, upwind sources of, say, carbonate dust or something that's like that? I mean, I know the um, Lost River Range isn't upwind of it for the most part, but there probably are other carbonate ranges that could bring dust in. Just because, with all the lake coring that I do mostly, when you're dating some of just the bulk organics, you can definitely get sort of a carbonate effect in the water system. So if you've got a carbonate dust source upstream, I'm just curious if that might play a part in that.
That's totally a possibility that honestly I hadn't really thought about that much yet, but is a great point, especially because the pioneers are kind of this metamorphic core, but like all of the ranges around it are sedimentary ranges. So it makes sense that you would have some nearby contribution for sure.
I sort of wonder if maybe if you just went and looked at the dust on the snow late season or something like that, in like late spring, early summer, something like that, and see if there's a significant carbonate source on the snowpack, maybe that would help explain part of
That's a
it.
great point. We're going back out in June, so I'll try to grab some snow samples while we're out there.
Fun stuff. Anyway, great stuff. Good job.
All right, great. Thank you, everybody. Thanks, Liv, for that talk and for the discussion. Let's move on now to our next speaker. We have Alex Takoudes up next from Middlebury College. And Alex, can you share your screen?
Yeah, let me get it up there.
Okay, while you're loading that, I will introduce you. Alex Takoudes recently graduated from Middlebury College with a bachelor's degree in Earth and Climate Sciences. For his undergraduate thesis, he combined his experience with machine learning and remote sensing to automate the process of mapping rock glaciers in the western U.S. He was advised by Al Handwerker from the NASA Jet Propulsion Laboratory and Jeff Monroe from Middlebury College. Outside of his studies, Alex raced mountain bikes with Middlebury's cycling team.
Great, thank you, Ben.
All right. Let's see. I don't think we're seeing your screen just yet, Alex.
Yep.
All right, should be all set. Take it away.
Sweet. Okay. Well, thank you, Ben, for the intro, and thank you all for being here on a Friday afternoon. I'll try to keep this short and sweet. I know it's perfect weather here in Oregon today, so yeah, I guess this is a presentation that's kind of been repurposed from my undergraduate thesis at Middlebury College. I just graduated this February, and this was a one-year thesis, and I'm pretty proud of the results I achieved, so I thought I'd share them. And hopefully this can be like a little lesson for anyone who hasn't done machine learning and kind of how it works. And if you've been using like machine learning data sets, it might be kind of fun to know how they're made. And if you're looking to getting into it, this might be a good intro. So yeah, this work kind of started in the field with Jeff Monroe. He took me to the Uintas in Utah my freshman semester, first summer I'd been on campus, and kind of took me out on the rock glaciers that he was researching with some senior thesis students. And it's kind of been fun to see this project come full circle my senior year to kind of wrap up a thesis on this. So without further ado, let's get into this. So, okay. So phase one is talking about rock glacier inventories. So thank you, Liv, for the great refresher on what rock glaciers are. I can keep this kind of brief, but I just wanted to show these great drone shots from Jeff and Al's recent paper that just kind of show that up close, really high resolution shots of different types of rock glaciers, highlighting their ridge and furrow topography, their kind of signs of downslope movement, and those oversteepened frontal lobes. And I love this quote: "The rock glaciers are the visible expression of cumulative deformation by long-term creep of ice debris mixtures under permafrost conditions." So that's kind of what we're going to get at today, is how do we pick up on that visible expression from satellite imagery? So why do we care about rock glaciers? Their hydrological significance is pretty well understood. So active rock glaciers can contribute, active rock glaciers with internal ice can contribute less than 5% of dry season groundwater discharge, which doesn't seem like a lot, but could become more important under warming conditions. And Jeff estimates that they contain a water volume equivalent of 10 to 35% of annual runoff in the Uinta Mountains. So similar figure to like what Liv was making in the bottom left here, that yellow ice is the internal ice of rock glaciers. So we're going to be focusing on active rock glaciers today with that internal ice, and ignoring the relict ones that have kind of stopped moving. And we also care about them for the biosphere as, refugia for cold adapted plants and animals under climate warming. We saw a bunch of pikas when we were in the field, and I'm sure anyone else who works on rock glaciers always sees these pikas running around. So let's talk about the different ways to make rock glacier inventories. So the most common way that everyone's probably familiar with is manually outlining Google Earth imagery. So here you can see a textbook example of a rock glacier with someone that's drawn an outline around the rock glacier here. And that's going to be your textbook way of doing it. And then you can kind of take that to the next level with two previous Middlebury theses, and lots of literature out there. Quinn's literature is published in 2021, where they used velocity maps from INSAR to refine their rock glacier outlines and delineate between what's actually an active rock glacier and what's an inactive rock glacier, because the velocity maps let you see what's moving. Now, I would like to highlight what these two manual inventories, I thought this figure from Rouillet in 2025, so kind of a preprint here, was pretty cool, where they showed a bunch of different rock glacier outlines from several operators. So looking at those dashed lines, you can see they're kind of all over the place and there's lots of disagreement. And that's kind of the whole story behind why we're trying to use deep learning to automate this process, is because so many people can have different interpretations of rock glaciers. And the hope is that we can take all of that knowledge and everyone's different interpretations of a rock glacier and combine them into a model that can kind of make that judgment for us and use everyone's knowledge together. So the third way of making a rock glacier inventory is using image segmentation with deep learning. And so let's get into what that is and what image segmentation is. So if you haven't done machine learning before, this is a very simple example where this is, let's say, for example, we have a data set from Spotify. Spotify has some fun data here. So they'll have song length, loudness, and danceability of the data. And let's say we have the artists associated with that data. So we can show this data to a computer and let it try to understand what song length, loudness, and danceability are associated with the different artists. So you can see there might be some trends here between AC/DC being louder than the Beatles and having longer songs. This might not be accurate, but just kind of take it as an example here. So pretend this is a training data set, and then let's pass this to a computer, pass a new data set to a computer. When we pass that new data set to the computer, we're going to hide the artist, so it doesn't know who wrote the song, and we're just going to show it the data and let the computer decide who wrote the songs. So it'll predict the Beatles and AC/DC here. So very oversimplified example, but it's pretty much the same concept when we apply it to imagery. So the images here are your song length, loudness, and the danceability, except it's just images with 2 dimensions and a bunch of pixels. And then your artist is the outlines. So your AC/DC and your Beatles. So what we're going to try and do is outline what we think is a rock glacier from the images. So this is called segmentation. And if you've ever done machine learning before, you don't have to have done it, but if you have, you might have heard of image classification, which is a slightly different problem where you're having a computer decide, yes, this is a rock glacier, or no, this is not a rock glacier. And that's a little bit of a simpler problem because you just pass the computer little squares of images and it can make that yes or no decision. In our case, we're trying to make it draw that outline, which is a slightly harder problem. And we also don't want to just feed it images of rock glaciers. We want to feed it images of anything and let it draw an outline. So just give it a whole region and let it draw those outlines. So what we're going to do is use something called a UNet architecture to train a convolutional neural network. So the UNet architecture is used for image segmentation and specifically medical image segmentation. So you can see some examples here. These are some different types of cancer or tumors or cells or parts of the body. And so they've pretty much created a model that can outline these images, and it'll produce a pixel-wise prediction. So each pixel specifically says, yes, this pixel belongs to a tumor, no, it does not. The reason why the UNet architecture is great is because it excels at precise localization of features, which we can use to our advantage in remote sensing to precisely map where features are. So if you haven't done machine learning before or any computer science, all you need to know is that it takes an image, the UNet architecture takes an image as input and creates a binary mask as a prediction as the output. Now, if you have done machine learning before, I'll briefly try to explain what's going on in the middle here, just so that if you are using papers like this or kind of curious how these papers work, you might know a little better after this talk. So essentially what we're going to do is have the computer apply a series of filters to an image to make those predictions. So how do we make a computer see this house? Because as humans, we can see this right away. But for a computer, we're going to have to kind of play with the image to let it see that. So let's imagine that on the right here, we have an image that's a series of pixels and we're zoomed in on a window of the house. Now, what we can do is take a filter that's on a 3x3 grid of pixels. So that's your filter on the right there. And then we're going to place it in the image in that yellow box. And that filter is looking for a certain pattern. So it's looking for, in this case, a right angle. And it's going to look at that 3x3 grid and assign a score to those pixels based on how well it matches that shape. So in this case, that first set there in this top left corner isn't going to get a very high score because it doesn't match that right angle shape. But we will slide that filter one pixel at a time and slide it across the image, and basically we'll end up with an image that has a bunch of scores based on how well each pixel matches that shape, or each set of pixels matches that shape. Then we can take other filters looking for different shapes, like a cross or a different right angle, and slide those filters across and have another image with a series of scores. Then at the next layer of filters, we're going to look for more abstract shapes like windows or doors or roofs. And those will be made up of the right angles, the crosses, and the other types of right angles. And then at the final level, this is all kind of abstract and not exactly how it's working, but at the final level, we'll be looking for shapes like houses, skyscrapers, or like a one-story building, which the computer can see by the assemblage of windows, doors, and roofs. So at a very high level, that's what's going on here with the model, and that's how we're going to find these rock glaciers from an image. So there are already pre-trained models out there. Meta has a great model called the Segment Anything model, where they've already done all the heavy lifting, and you can just do something like on the left here, you can see a horse. You can just pass this image to the model, and it'll outline where the horse is. Or even better, on the bottom, you can see this looks like a self-driving car, where it's outlining where the cars are, where the trees are, and where the roads are. Now, the problem with this is that a pre-trained model like the Segment Anything model doesn't exactly know what a rock glacier looks like. It's going to look at a satellite image and segment the rocks from the trees, from the water, all the things that are really easy to pull apart. But rock glaciers are really hard to pull apart from the terrain unless you know the topography that you're looking for. So we need to supervise a model and use a large volume of imagery to train that model. That uses a lot of computing resources. So we're going to use Google Drive and Google Colab to just use cloud computing and not have to use a big computer. So what this research actually kind of added to the literature, which is really cool, is that we used a bunch of input layers. So if you've ever looked at a satellite image, you're only seeing 3 bands of a satellite image. That's red, green, and blue. And here you can see that comes from the Sentinel-2 satellite. In this case, that's what we're going to use for the optical imagery. And that's all you can see in a computer screen because your computer just has red, green, and blue channels. But because we're training a computer, we can give it as many layers as we want, and it'll see all of them at once. As a human, we could click through these layers, but the computer can take them all at once, which is really cool. So we're going to use all these different spectral channels from Sentinel-2. We're going to use thermal data from Landsat 8, digital elevation models, and some Sentinel-1 SAR backscatter imagery. We didn't end up using velocity maps because of the limitations of the cloud computing. We couldn't actually create large enough scale velocity maps for this model. So this is the first study to apply this many bands to rock glaciers, which is really cool. So here's my high-level workflow. We're going to take a manual inventory and turn them into outlines. And we're going to take all the satellite data and create something called the stack. We'll train a data set, calculate accuracy, make predictions, and then process those results. And you can see I used Google Earth Engine for all the satellite imagery and Google Colab to train the model. So I'd like to briefly mention how I calculated accuracy, and then we'll get into some of the results. So I'm going to use a metric called intersection over union to calculate accuracy. So intersection over union measures the amount of overlap between 2 objects. So in this example here, let's say the model made the yellow outline as a prediction for a rock glacier, and the blue is what the actual rock glacier is. So in this case, the white pixels are correct. They're a true positive. The red pixels are where the model missed, and the green pixels are where the model overpredicted. And we want to make sure we penalize the model for both missing and overpredicting. So in this case, the math is white pixels divided by white pixels plus green plus red. And that gets us an IOU of 0.6 or 60% accuracy, which kind of makes sense in this case here. So if you see in the results later on, I'll be mentioning IOU. That's just how accurate the model is. So here's the study region. We're in the Uinta Mountains. Quinn Brencher and Cameron Klutmeyer have done previous thesis work here. Jeff and Al have been studying these mountains for years. So it's just a great local knowledge area that we can ground truth our predictions with. And this is me in the field with Jeff my freshman year. And there's Jeff's truck. So here's the scale of my training regions and my testing regions. So any training region is in dark blue. And you can just see, this is actually, Liv mentioned this Johnson et al. Inventory from 2021, where they manually mapped every rock glacier in the US. Pretty much they manually mapped 10,000 rock glaciers, which makes the perfect training inventory for a deep learning model like this, because you want to use a bunch of input data. And so I fortunately didn't have to do any manual mapping. I could just train the computer to do it. You can see I also have testing regions spread out around the Western US. And I'll also mention that I am going to use the INSAR inventory from Quinn Brencher to just kind of evaluate the results. So if you've been kind of checked out, this is kind of where it all comes back together. This is what the model did. The yellow outlines are what the model predicted, and the blue outlines are the ground truth from Portland State, the Johnson 2021. So it's hard to see from here without the satellite data, but it clearly did well in some spots, not so well in some other spots. Let's see some examples. So here's some really accurate examples from the model. You can see IOU equals 0.83, IOU equals 0.82, and you can see the outlines really match up here. Now, what was surprising about these results is these rock glaciers, in my opinion, are the hardest to differentiate from the landscape. These low bait rock glaciers, which really kind of just blend in with that hillside topography, as opposed to a tongue-shaped rock glacier that's got a nice flow down below a talus slope. So it was really impressive that the model excelled at mapping these low bait shaped rock glaciers. Now, here's an example of where the model was technically wrong. You can see the yellow doesn't overlap with any blue, but it actually overlaps with the Brencher white INSAR inventory. So this kind of just highlights the fact that there are differences between manual inventories, and it's hard to evaluate this model just based on the Johnson inventory. Here, again, it was technically wrong. If we evaluated with the Brencher inventory, it might have been correct. So it's kind of up to judgment with how accurate your model is. So looking at some regional results, this I'll kind of breeze through here, but I think what's important to note is this IOU column. You can see the most accurate region was in Utah. Or actually, sorry, by state, it was most accurate in Utah, but that was only for one region. Now, the most accurate specific region was in Colorado with an IOU score of 0.518. This was the most precise region in Montana. So this is where it was not, it was missing the least amount of rock glaciers. It wasn't making too many over predictions. And then here's an example in Wyoming in the Wind River Range where the model was thrown off by a bunch of snow and ice glaciers. And so its accuracy scores are really low. So this brings me to my conclusions. Conclusion one is the model worked and it was 50% accurate according to the Portland State inventory. Like I said, that's based on your judgment. So if we evaluated between the yellow and the blue, we got 50%. Between my model and the Quinn Brencher model, I got 42% accuracy. And then just for kicks, I evaluated the Quinn Brencher model or Quinn Brencher inventory to the Portland State inventory and got an accuracy of 41%. So technically I was more accurate than Quinn's manual inventory, but again, that's all up to your judgment. And it's hard to say just based on the numbers here. Conclusion two was that adding more bands increased the model's accuracy from 21% to 50%. And those are those 14 layers I showed. So I've settled on this final model here with 14 bands. Conclusion three is that accuracy improved from 38% to 50% when the model had already seen rock glaciers from the region where it was predicting. So it would be good if you're going to make rock predictions in a new region, it might be nice to give it some examples of what rock glaciers there actually look like, since there are so many regional differences in the color and shape and topography of rock glaciers. That it's very helpful to know kind of what you're getting into in a region before the model has to make predictions there. And conclusion four is that the model, kind of as expected, did struggle with similar rocky landforms like debris-covered glaciers, ice-cored moraines, and talus slopes. This is in the Wind River Range again, where there were a bunch of ice glaciers and ice-cored moraines, and all of these yellow outlines with no blue near them were all false positives. So all of these were kind of failed predictions according to the model. So that brings me to future research where I think it would be beneficial to just use more training data with more powerful computers, as is true with all machine learning models, incorporating negative outlines saying that a debris-covered glacier or ice-cored moraines are not rock glaciers might be helpful. And then it might be cool to create a comprehensive inventory of Utah based on deep learning. And here are my sources. And if you've ever used this, you can just kind of scroll around on my results here in Google Earth Engine. So thank you all. And yeah, happy to take questions.
All right, excellent. Alex, that was really very interesting to learn about. We have plenty of time for discussion. If somebody wants to turn on their microphone or raise their hand, go ahead. Philip, I see you first. Go ahead.
Hey, Alex, I think this is a fantastic work. I think it definitely indicate the trend of machine learning on this. So I have several questions. One is why you use UNet? I think they have a lot of other kind of deep learning methodology, for example, CNN or DNN kind of thing. Why you use this? Another thing is, are you mainly using satellite imagery for the training for the identification of this? Did you consider using DEM or DEM derived features for this work? Okay.
Yeah, thank you, Philip. Yeah, so if you are familiar with the literature, there's actually not a lot of papers out there that use a UNet. This is kind of a I think the most popular model I found was that everyone was using something called the Deep Lab. Let me see if I might have a bonus slide in here where I compared my results with the Deep Lab. But I did try that model. I think there's been comprehensive inventories of the Tibetan Plateau in China, and they did that whole inventory with the Deep Lab. And I did try that, but I found that I was getting better results with the UNet, so I ended up sticking with that. It's possible that the Deep Lab just had more training parameters, and I wasn't giving it enough data to make accurate enough predictions. I think that was one of my limitations, was that I wished I could have used a larger training region, and I was just kind of on that cusp of, is this really enough data for the model to not overfit? So yeah, Deep Lab was considered, and I found the UNet was better, and I would be curious if there were to be a paper in the future that really compares the results of these models and which one's doing the best.
My suggestion is, if you write this up, maybe you can add a comparison with Deep Lab, because Deep Lab use a lot. Mm-hmm.
Yeah, absolutely. And then with regards to layers, this was kind of this was one of the things I never fully got to answer in this thesis, and maybe if it was a PhD or a dissertation, I might have. But I did use 14 layers, but I didn't really know. I didn't end up finding out which one was the most important. And I wish I could have gone through, and whether it was just removing one layer at a time and comparing how the model did, or somehow just evaluating what was the most influential input layer here, because I'm not sure if it was the satellite imagery or the thermal imagery or the DEM. I wish I had kind of known. All I know is that using more of them made the model better.
Okay. Is the UNet, the input is based on the image format, right? The 3-band image format?
That's right. Yeah, the version
So
I was using.
You have an option to do multiple combinations to test which one is more efficient.
That's right. Yeah, and I'm not super familiar with the underlying code of how the models are built, but essentially my code did let me customize the inputs to be 384 pixels by 384 by 14. So I was using a 14-band image as the input.
Oh, that's good.
Yeah. Yep.
Yeah. Thank you.
Thank you.
All right, Glenn, go ahead.
Yeah, Alex, really, really fun talk, and my mind is spinning here. But at one point, you talked about some form of success accuracy. I can't remember exactly what your measure was there. on a state-by-state basis. And do you know, I think you said Colorado was your most successful prediction, state for prediction. Do you have any idea why that was, and why, I think you said Wyoming, probably because of snow and ice glaciers, but can you speak a little more to that?
That's right. Yeah, I kind of skimmed over this section because it's funny, I left this out of my thesis presentation because I thought the table was too much, but I figured this group could handle some numbers with some tables. So let me put them all up at once here. It's hard to see without the background imagery, but pretty much any best performing region was shown in bold here. So you can see these two regions in Colorado way outperformed any other region. And I think my hunch on that was that there was the highest density of rock glaciers there. So the model had seen most of its rock glaciers from Colorado. And there's also just no ice or there's no snow in those images to throw it off. Even in the Uintas, so this is region 1 here, I did start to see some snow and ice at higher elevations. And I think that was kind of the determining factor of what was making the model better or worse, was snow or ice influence.
Thank you.
Yeah.
So I guess, Alex, given that, if somebody were to go out to an area like, say, the Sierra Nevada, where there are, plenty of rock glaciers, but also lots of ice too, lots of snow, how would you recommend designing a training data set for something like that, if somebody wanted to make an inventory there?
That's right. Yeah, I think the most important part of that would be incorporating negative outlines of what isn't a rock glacier, because there are so many potential false positives in a region like that. And I think I just didn't know, literally just down to the code, I didn't know how to incorporate something like that. But the literature is out there that does that. And I think everyone's kind of found success with incorporating those negatives. And I mean, I think one other kind of important thing to highlight here is it is valuable, in my opinion, and based on what I saw, to include training data sets from a broad region, even if you're going to somewhere that's not similar to those regions, just because then you've shown the model, it already knows kind of how to delineate rock glaciers, even if it's not that specific color or anything. You might want to go into the Sierra Nevadas and outline a few, this is a rock glacier and this isn't a rock glacier, to also feed to the model. Yeah.
Very good. Yes, we need to avoid this Wyoming problem. I think that's what you're saying.
That's right. Yeah, so I'm excited to see the future of this. And like I said, this is just an undergrad thesis, but there is a ton of exciting research now. And yeah, hopefully machine learning will bring some huge improvements to ice glacier mapping and rock glacier mapping in the near future here.
I think one potential is to use this to do the marine mapping. So that will be important for us.
Absolutely. Yeah.
All right, great. Well, I think we just hit the top of the hour here. I think Alex deserves some special recognition for being the first to present an undergrad thesis in this series. So very good, and thank you again, Alex. Thank you, Liv.
Thank you.
Just fantastic work by both of you today. Appreciate you being here. And if you change your mind about the recording, let me know. Otherwise, I'm going to put this on YouTube for the rest of the group to check out. Also want to mention before we go away, we do have one open space in the schedule next Thursday because we had a postponement. So if anybody is wanting to try out a talk or just share some research or has a student or something like that, we can fit someone in on short notice next week. So just let me know. Thanks again to our speakers. Everybody, thanks for being here, and we'll see you next week.
Thanks, everybody.
Thanks, everyone. Thanks, Ben.
Thank you. Thanks, everybody.